So we're going to be talking about precipitation reactions. The thing you need to keep in mind with precipitation reactions, those are going to be reactions that involve formation of precipitates or formation of a solid as one of the products in a chemical reaction. Before we get to that, though, you need to recognize that there's going to be three main types of chemical equations we're going to worry about. It's going to be precipitation reactions, acid-base reactions, and reduction-oxidation or redox reactions. Now, the first two types of these reactions are going to deal with double displacement. So we're going to talk about what that double displacement means, and what it's referring to is something called metathesis reactions. So in a double displacement reaction, so if we start with an AX plus BY, A being a cation, X being an anion, B being a cation, Y being an anion, and those are reactants, when we form our products, we're just going to switch the anions around. When we do that, we form new compounds, but in order to have a reaction occur, we need to have one of three things happen. We need to form an insoluble solid, or a precipitate. That'll involve precipitation reactions. We'll form an insoluble gas, or we'll form weak or non-electrolytes. A weak and non-electrolyte for like an acid reactor in the base, water is going to be a weak electrolyte. So if we form liquid water, that means a reaction has occurred. All right, so in order for these metathesis reactions to actually occur, we have to have one of these three things formed on the product side. So let's look at a little bit more about swapping those anions in an example here. So if I start with K2CrO4 and mix it with BaNO3 okay, that's in the first beaker on the left there. You can see the different atoms and ions down there. If I want to predict what products are going to be formed, first I need to predict what ions are formed from those compounds. So I'm forming K plus and CrO4 2-. I'm not worried about the numbers of those right now. Okay, I'm not balancing the equation yet. All I'm going to do is see what ions are formed and then create the new compounds from that. So for barium nitrate, it'd be Ba2 plus NO3 1-. And then what I'm going to do is I'm going to switch the anions around. So K plus is going with NO3-. Ba2 plus is going to go with the CrO4 2-. Once I know which anions are going together, I need to write valence formulas based upon their charges. I don't just add them together. I have to balance their formulas. And I don't want to look at the number of atoms. I'm not, once again, trying to balance the equation. All I'm trying to get is balanced formulas. So if I have K plus and NO3- combining together, I'd get KNO3, Ba2 plus and CrO4 2- combined together, I'd get BaCrO4. Once again, I'm not worried about number of atoms on the left, number of atoms on the right yet. I want to get my formulas first. Okay, now if you look at the picture, the beaker on the right kind of shows the combinations of those. Okay, and it turns out that the BaCrO4 would be a solid. That's why it's located on the bottom there. And so that would mean we have a reaction occur. Okay, we're not worried about that yet. But once we have the KNO3 and the BaCrO4, then we'd go through and balance the overall equation, and we'd end up with two KNO3s because we have two potassiums and two nitrates on the left-hand side of the equation. Okay, but let's worry first about predicting these products. Then we'll combine it with balancing the equation. All right, so let's look at a few more examples of this. So, in looking at these reactants combining together, if I separate them up into their ion forms, then I switch the anions, then I'm going to recombine them and form new formulas from those ion combinations, those new ion combinations. But I have to make sure it's balanced based upon those charges. Okay, once I've done that, then I could go through and balance this equation. And once again, I'm not worried about that right now. All I'm worried about is predicting those products. So let's look at the next one. Break everything up into its ions. Switch the anions around. and then make new formulas based upon those new combinations of ions. All right, hopefully you're getting the idea of this, but it can get a little bit confusing, a little bit complicated, so we're going to run through a couple more. And the last one here. So you can see here, I'm writing everything out. I'm figuring out the ions first and then recombining them to get the balanced formulas first before I even consider balancing those equations. So these equations aren't balanced. All we're worried about right now is predicting what are the new formulas of those end products. Okay, you've got to understand how to do this. Also, it goes back to understanding how are these things going to form ions, or what ions are going to be formed from these initial starting formulas. You've got to understand that as well. So that's going to be a metathesis or double displacement reaction. That AX plus BY goes to AY plus BX. Okay, now we're going to get into the specific one of precipitation. So with precipitation reactions, we can look here at an example. If I take potassium iodide, which is soluble in water, it's aqueous, and I take lead 2 nitrate, which is soluble in water, it's aqueous, swap the anions around, write balanced formulas from those anions, I get KNO3, which is aqueous and soluble, plus PBI2, which is going to be insoluble, it's going to form a solid. So things that are going to be soluble are going to be aqueous, things that are going to be insoluble we're going to write as a solid. Okay, and through the pictures here you can kind of see what's going on both at the macroscopic level that we can see and what would be occurring at the atomic or molecular level that we can't see. In order to figure out what's going to be soluble and what's going to be insoluble, we're going to have to follow some solubility rules. Now, you'll have access to these for an exam. You should know how to use this table, or if you've got another set of solubility rules you want to pull out, that's fine. You need to know this table well enough that if you're going to use it, you can use it rather quickly. Okay, but these solubility rules are going to be uniform across multiple tables. The tables themselves may look different, but they're going to tell you the same things. Okay, so in this particular one, we're going to look at the top half of the table first. Now it says compounds containing the following ions are generally soluble. That means they're going to be aqueous. They're going to dissolve in solution. So if we look at the first row there, group 1 cations and NH4+, those are all going to be soluble. And any compound made with those is going to be soluble. So if I have a group 1 cation combined with any other anion, I'm going to write aqueous for the form of that species in my chemical equation. Now if you look to the right of that, under the title exceptions, it says none. Well, there's no exceptions to that. That's always going to be the case. Go to the next one. We have nitrates and acetates. Those are all going to be soluble. Exceptions, we have none of those. Next, we have chlorides, bromides, iodides, the halogens. All of those are going to be soluble, and when we look at the exceptions, though, there are some things that are going to form from it that are going to be insoluble. So if any of those ions pair with silver, mercury, or lead, those compounds are going to be insoluble. Right? That's what those exceptions mean. And then sulfate, all sulfates are going to be soluble with the exceptions listed there. Okay, those exceptions are going to be insoluble. They're going to form solids. That's the top half of the table. When we go to the bottom half of this table, those concepts kind of switch. Okay, so now on the left-hand side, anything that combines with those ions are going to be insoluble. They're going to form solids. The exceptions are going to be soluble. Okay, so hydroxides and sulfides. those are going to be insoluble compounds. If you have hydroxide or sulfide, you can put down a solid for that form unless it's one of those exceptions. So if lithium, sodium, or potassium are combined with hydroxide, it's going to be soluble. If calcium, strontium, or barium is combined with the sulfide, that's going to be soluble. It's going to be aqueous. Okay? And then carbonates and phosphates are going to be insoluble. They'd form solids, except for those things listed there. All right, so you need to understand how to read this table and how to use these rules, because the next thing we're going to do is predict phases of these products. So let's go back to first couple of examples here. We had the iron 2 sulfate reacting with the potassium chloride to form iron 2 chloride, potassium sulfate. Once we predicted the formulas of the products that are formed, we then need to predict their phases. Well, if we look at the solubility rules table and apply those rules, iron 2 chloride ends up being aqueous. Potassium sulfate ends up being aqueous. The reason why it's important to identify the phase of these end products is because now we have to look at this reaction and decide, has this reaction actually occurred? Does anything actually happen? Well, if everything is aqueous in the reaction, we're going to have no reaction. Nothing happens when we mix iron 2 sulfate and potassium chloride. In order for a double displacement reaction to occur, we need to form a solid, liquid, gas, or weak electrolyte. None of those were formed, so this would technically be no reaction, or I use NR to represent no reaction. Nothing would have happened. We'd have just mixed two solutions together and ended up with a new mixture. Okay, let's look at the next one. We've got the aluminum hydroxide. If we go back to the rules, turns out that's going to form a solid. The barium nitrate, we look at the rules for that. That's going to be aqueous. Well, now we've formed a solid as one of our products, so we definitely know we have a chemical reaction occur, and it's going to be a precipitation reaction because we formed a solid. We formed a precipitate. All right, let's look at the calcium chloride reacting with the sodium sulfate. When we look at the rules and apply them to calcium sulfate, we get a solid. Sodium chloride, it's going to be aqueous. So we know a reaction's occurred, and it's a precipitation reaction because we formed a solid. All right, the next one, let's look at the nickel 2 chloride formed. That's going to be aqueous. The sodium nitrate, it's going to be aqueous. So that would be a no reaction. So we've looked at predicting end products. We've looked at predicting their phases. We would then, before we do anything else, ideally balance those equations. We've already gone through balancing equations, though. I'm not going to go through that here. And we'd end up with these overall balanced equations. Now, because we're dealing with aqueous solutions, another thing we're going to look at is something called ionic equations. With ionic equations, we're going to start with first having a molecular equation. Molecular equation is exactly the type of equation we've been talking about before. Okay, it has everything combined together, shows all the phases, it's properly balanced. But what we can do is we can actually look in this solution to see what actually is occurring, what actual chemical reaction is going on. And to do that, we're going to take everything that's aqueous and break it up into its ions. We are not going to break up anything that's listed as liquid, solid, or gas. And we're not going to break up any polyatomic ions. When we do that, we're going to get something called the complete ionic equation. So we're going to show all the ions that are present in these solutions. So if I take HCl, it breaks up into H plus, Cl minus. Take NaOH, it breaks up into Na plus, OH minus. If I take H2O, it's a liquid, it doesn't break up at all. If I take sodium chloride, it breaks up into Na plus, Cl minus. Now that's the complete ionic equation. It's showing all the ions involved. But if you notice, we have some ions that we start with on the left-hand side, the reactant side, that we end up with on the product side. Well, if they're both in the reactant side and the product side, nothing has happened to them. So what we do is we get a new equation that we're going to call the net ionic equation. And we're going to remove something called spectator ions. Spectator ions meaning that they're there, but they're not actually going through any change. They're not part of an overall chemical reaction. So things that are on the reactant side that are the same as on the product side, those are spectator ions, and we can remove them. When we remove the spectator ions, we end up with just H plus aqueous plus OH minus aqueous going to form water, liquid. That is the overall equation, the overall reaction that's occurring, is really just that H plus the OH minus combining to form water. The Na plus and Cl minus are still there, but they didn't do anything. We started with them dissolved in solution, we end with them dissolved in solution. So these type of equations we can write out for these aqueous ionic reactions, so that we just get it down to what ions are actually involved in the reaction. Now another thing to keep in mind when we go to break things up into their ion forms, the other thing too is only strong electrolytes are going to be written in ionic form. So if you know you have a weak acid or a slightly soluble compound, we wouldn't break those up into ions. Okay, that's a minor thing, but it's something to keep in mind as we go through the rest of these.